This video is about a very important concept in differential equations, the concept of something called a slope field. It's a concept introduced in Chapter 1, and it's sort of a precursor to an even more important concept of something called a vector field. But we need to understand slope fields first before we can understand vector fields. So what is a slope field all about? Take a first order differential equation of this form. This is the form typically seen in the book. dy dt equals some function of t and y on the right side. We have a dy dt solved for on the left side. Again, sometimes your equation might not look like this initially, but if you can put it in this form by solving for dy dt, then it's something that you can apply this idea to. And the idea is this. Create a plane and label the axes with t and y. And for any point in this plane, whose coordinates we can also label with t and y, we create a little line segment whose slope is equal to the value of this function on the right-hand side at this point t comma y. So let's just pretend, for the sake of argument, that when I plug in this particular point into this function on the right-hand side, that I get a value of 2. I would make a little line segment centered at this point with a slope of 2. If f of that point, f of t comma y equals 2, then the slope, not the height or anything like that, the slope of that line segment is 2. And I imagine doing that at every single point in the plane. Now I can't literally do that, of course, because there are infinitely many points. But I can certainly do it at a finite number of points, mark off a bunch of little points and corresponding line segments with slope given by f of t comma y. And maybe I get a picture like this. Some of these slopes might be negative, some might be close to 0 or equal to 0. I might get some kind of picture like that. How is this related to differential equations? Well, think about what dy dt gives you. dy dt is the derivative of the unknown function y. And so what you're saying is the derivative at any given point is equal to the value of this function at that point. In other words, the slope of the graph of this unknown function at any point that it goes through equals the value of this function. What that means is that anytime a solution passes through one of these points, like this point over here, the slope of the tangent line at that point has to be equal to the same slope that this little line segment has. And because of this fact, this very fundamental fact, it allows you to draw in approximately what solution curves will look like if you've drawn enough line segments in the slope field. And so, for example, we might have a curve that looks about like this. If we sort of follow the slope marks as our direction, giving us an approximation to a solution to this differential equation. We can kind of eyeball it. This is best done on a computer, and these transparencies that I'm going to show you next are done with the independent variable being x instead of t. That's okay. The idea is the same. I'm going to start with the differential equation. dy dx equals x. Actually, that's a differential equation that we can solve very easily. Well, what it's saying is we're looking for a function whose derivative is always equal to x. I can even write down the general solution very quickly. Just integrate. The answer is y equals 1/2 x squared plus c. That's the general solution. Then you can solve any initial value problem that you want. In other words, the graphs of solutions to this thing are parabolas that open upward. And in fact have a vertex that's going to be on the y-axis. The minimum is going to occur at x equals 0. If we graph the slope field with a computer, it ends up looking like this. Kind of pretty. Does it make sense? Yes, it should make sense. At any point, say I take this point right about here, the slope of the little line segment should be equal to the value of the right-hand side. Remember, we're using x and y instead of t and y there. That's my function of, well, really just x, but I'll go ahead and put a comma y in there anyway, to emphasize that I could have a y on the right-hand side. At any point, I find the x-coordinate of the point, and that x-coordinate is going to be the slope of the little line segment that I make. So, I don't know, this line segment, the x-coordinate of that point might be 1. It looks like the slope is about 1. The x-coordinate of these points along this vertical line is about 2. And in fact, it looks like all those line segments have a slope of 2. This hints at something else. Because this right-hand side only depends on x, this slope field is going to have line segments with the same slope along any vertical line where x is constant. If you draw a bunch of vertical lines in here, no matter where you draw the vertical line, you can see that all the little slope marks, mini tangents to solution curves, all have the same slope along those line segments. And when we try to follow those tangent lines to sketch solution curves, say something like this, we can see that we get a function whose graph does look like it certainly could come from that equation right there. We get lots of different ones because there are lots of different values of c that we can use, infinitely many. They're all vertical translations of each other. They all differ by a constant when your right-hand side only depends on x, or if we're using t for the independent variable, when it only depends on t. Here's an example where the right-hand side only depends on y. dy dx equals y. Or I could have written dy dt equals y. Take a moment to think about that. The slope field for that one's going to have to be constant along horizontal lines where y is constant. In fact, if you look at it, get a computer to draw it for you, it looks like this. Where y is positive, above the x-axis, the slope marks are certainly positive, and as y increases, the slopes increase, and they are constant along horizontal lines. The vertical and the horizontal lines that I'm drawing in the previous one and this one are not graphs of solutions. They're just illustrating that for the previous one, the slope marks had constant slopes along vertical lines, and for this one, you've got constant slopes along horizontal lines. But once again, the principle of drawing solutions based on following the slope marks in such a way that when you pass through the middle of one of these line segments, the curve has the same slope as the line segment does. The line segment is really a little tangent line to solution curves as they pass through them. Gives you solutions that look like this. And down here below the x-axis, they have to go down. And if you think about it, when y is 0 and you're on the x-axis, the slope has got to be 0. That's an equilibrium solution. It's a constant function which solves the differential equation. Let's see if we can find a symbolic form for the solution to this. dy dx equals y, we're looking for a function whose derivative always equals, well, not y, at least when you simplify it, it shouldn't equal y, but Think of y as representing the function. We're looking for a function whose derivative is equal to itself, like e to the x. Or in fact, the general solution is any constant times e to the x. These functions are not vertical translations of each other. They're actually horizontal translations of each other. How could you prove such a thing? Well, you might recall that if you replace x with, say, x minus 2, for example, that shifts the graph of e to the x to the right by 2 units. And that, by properties of exponents, can be thought of as a constant times e to the x. Therefore, that's why you can think of that function c times e to the x, where c is equal to e to the negative 2, as a horizontal translation of the graph of e to the x. And you can see it here visually here. Translate this one to the right by a certain amount, you're going to get this one right there. They're not all horizontal translations of each other, like this one's not a horizontal translation of that one. But certainly the ones up here are horizontal translations of each other, and the ones down there are horizontal translations of each other. This is an autonomous equation. The right-hand side only depends on y. Anytime you have an autonomous equation, you're going to get the slope field being constant along horizontal lines. And in particular, when you're looking for equilibrium solutions, where the right-hand side equals 0, the slope field will have a slope of 0, like it does at y equals 0 in this example. Let's do a slightly more complicated autonomous example. dy dx equals 2y minus y squared. That is autonomous. Thinking in terms of finding equilibria, if we factor that right-hand side, we see that it's got equilibrium solutions at y equals 0 and y equals 2. That makes the right-hand side equal to 0, and constant functions have a 0 derivative. So we would have those two equilibrium solutions, and in fact the slope field indicates this, although we're only looking in the first quadrant. This is at y equals 0 down here. It's along the x-axis. This is y equals 1 up here. You can see the slope marks are all horizontal. So you've got an equilibrium solution up there, an equilibrium solution down here. In between, solution curves either decrease or increase. And in fact, that's got to be the case in all autonomous equations. You either have, all solutions are either constant functions or always increasing or always decreasing, depending on what your initial condition is. We could also graph it for y being negative. This was not done here, but if you did, you'd get negative slopes, and your solutions would be decreasing down there. What about a mixture of x's and y's, or t's and y's on the right-hand side? That's the hard case. Even a simple looking equation like this, dy dx equals x minus y, could be very difficult to try to deal with. Could we solve this equation analytically? Well, you couldn't separate variables. That wouldn't work. Once you get to section 1.8, you'll see that this equation is something called a linear equation that can be solved either through a sophisticated kind of guessing called the method of undetermined coefficients, or through something called integrating factors. As far as the slope field goes, well, it's kind of a pain again to do by hand. You have to rely on a computer. There it is. This one's not constant along vertical lines. Look at vertical lines there, you see that the slope changes. It's also not constant along horizontal lines. There are some special features, however. For example, it looks like perhaps, well, unless this drawing is off a little bit, a function about like this might be a solution. It looks like there might be a straight line solution. What function might that be? Well, you might take a guess that perhaps it's y equals x minus 1. Perhaps. We have to be lucky. Are we lucky? Let's guess y equals x minus 1. The derivative of that is always 1. And x minus y, x minus the function, that's always 1, 2. So in fact, that guess is a lucky guess. It really is a solution. Other solutions for this non-autonomous equation sometimes are increasing, sometimes are decreasing. You'd have solutions that go like this, solutions that go like this. We can tell from the slope field, however, that it looks like they all have the property that they approach this particular solution, y equals x minus 1, as x goes to infinity. So that's something pretty useful, seemingly, that we can get from the slope field, which might be hard unless we have other techniques to see in any other way. Is there anything else we can remark about the slope field? I guess one other thing I'll point out is that you can figure out where the slope is 0. The slope is going to be 0 when the right-hand side is 0, when y equals x. Along this line, through the origin right here, the line y equals x, you can see that those marks have a slope of 0. They're not equilibrium solutions. Those are just slope marks with a slope of 0. So your solutions are going to have either maxima or minima at those points. In this case, they would be local mins. One last example. dy dx equals x squared minus y squared. There it is. This one is really crazy looking. What kinds of things can we see from it? Well, it's going to be giving us a slope of 0 when y squared equals x squared, which is equivalent to y either equaling x or negative x. So along this line with a slope of 1 through the origin, and along this line with a slope of negative 1 through the origin, you've got slope marks with the slope of 0. Those are not solution curves. What will solution curves look like? Well, evidently you'll have some that look about like this. This does get a little bit tricky. And even though these marks seem to indicate that you want to go kind of back toward that line y equals x there, if you think about it, it can't possibly ever get there because these still have a slope of 0. The slopes become positive very quickly. In between here, it's kind of subtle. I think what's happening is the slope marks are increasing in size very rapidly. So you've got to kind of be careful. There are some other solutions that appear like they're going to decrease. I need to be careful here. I need to make sure I'm doing this right. I think you are going to get something like this. Some will go down there. Some, if you're up high enough, will, well, maybe up here, will head back up this way. It's a very subtle and difficult thing to get it exactly right, okay, with an example like this. But we can get the basic gist of it with this kind of thinking. In the next video that I make about slope fields, I'm going to show you how to use Mathematica to think about and make slope fields, and also to use the CD-ROM. To finish this one off, though, well, this is not so much a joke as just something kind of funny. Sometimes you hear it said that, well, some teachers might say that nobody ever really truly understands math. They just get used to it. Well, I don't agree with that statement completely. I think you can truly understand parts of math, but it is also true that to get to the point where you understand things well, you have to just kind of get used to it in a sense. And sometimes that comes up with taking exams. You see a question, it looks really confusing. It's stated in a way that you're not used to. And I found a couple funny examples on the internet of, well, questions that were stated seemingly very simply. This question is stated, find x. What's going to follow? Well, it could be an algebraic equation, or perhaps x is a quantity in a diagram. In fact, that's the case here. X is a side of a triangle, and well, here's the student's answer. Here it is. And this next student was instructed, named Peter, was instructed to expand something. Typically, the word expand in math is an algebraic kind of operation. In fact, that's what this person, Peter, had to do, was to expand a plus b to the n. And if you've ever heard of the binomial formula, that's what Peter was supposed to use here, but Peter was frustrated, evidently, and expanded it in that way. That's it for this talk.